related to different color physics, but not tensor networks, and a way to also solve the Schrodinger equation in a particular way that goes beyond the standard methods like TDP that I presented to you in this conference. Okay, so as I said, the goal will be to solve the Schrodinger equation in an exploration in large table space. Using, so we have the common state, which is the large vector, and we know that the coefficient follows IHSI, which is the exponential large matrix. So of course you can do that exactly. And you know that you can do that using a functional ansatz, like a matrix of states. So that is basically a vector in that exponential large space that is described by a set of polynomially large parameters. And then once you have this ansatz, you can use an algorithm that will track iteratively the dynamics starting from the initial state of a certain system. So this is something iterative, but you also need to discretize the dynamics. So there are two things that is two problems. So one is the entanglement growth, that when you try to do quantum dynamics, if you reach very long time, the entanglement will grow in some system, and so it's a major bottleneck if you do something with the MPS, for example. And the other is that you accumulate error over time, because either you don't follow the dynamics properly in your parameter space, and also you have this thing of the discretization that can lead to factorization errors and so on. So we're going to use something else for it's not really essential to what I'm going to present, but it's called neural color space. So it's something that kind of goes beyond tensor networks, which is basically another type of ansatz based on neural networks that have more expressivity, so they can represent volume law states, for example, which MPS cannot. But they have also less structures. You can think it as a. So it's another way to represent an exponential large vector with a number of parameters, which is polynomial, but to lose some structure. So one of the main things that you lose is the ability to do exact contraction, for example, of the ansatz, which is very useful to compute accurately, for example, the dynamics or an expectation value. So we need to use Monte Carlo something, which is okay. So now I'm going to present what's going to be more of the core of the presentation. Is that now instead of having one ansatz that lives in the Hilbert space and that we evolve iteratively to solve the dynamics using the TDP, what instead now we consider time as an input of our ansatz. So imagine now you have an NPS where so these are physical legs and you have an expression that inputs the time. So this is not what we're going to use, but we can do the same thing with our neural color states, which is basically now we have the physical, the neural of input, not the time, which are the time dependent output, basically. So now instead of just working in the Hilbert space, we work in the space of trajectories inside the Hilbert space. Okay. And now that we have this tool, I suppose that we consider a space of trajectories to start at the wanted initial states from which we will solve the dynamics. One way to solve them is to minimize this function, which is basically the integrated error that you make on an interval to solve the dynamics. So here you have the derivative of the ansatz. Here you have the direction that you want to follow. And basically you will align both of the arrows at each point in time. And if your distance is 0, you know that you solve exactly the dynamics. Yeah. And why? So what is nice in our states is that we think how do we evaluate the subject. And with something, once you know automatic differentiation, you can directly compute it without resorting on discretization or this kind of thing. Okay, so now we have the what is the difference? So first, you recall that before I told you that to solve the dynamics, we were approximating the exact dynamics in the rational manifold. So we were approximating the evolution into the space of parameters. But the problem is that this thing can become accurate, and if you miss one step, in our method, then you are off for in the entire trajectory, and the rest of your evolution is going to be wrong. So here, in that framework, now the solution of the Schrödinger equation becomes the fixed point of the optimization, which means that if you make a mistake at one step of the optimization when you try to minimize this loss, it won't matter because the dynamics ultimately will, if you are able to minimize this loss, you will be able to solve the dynamics. And also, it's not a sequential computation, which from the point of view of neural networks is pretty interesting because there are a lot of issues to do parallel computation, but if before in the TDP you were constrained to one time at a time, and if you have, for example, very small time steps to go to very much time, it would be very expensive. Whereas here we have a middle. Okay, and also this plot directly tells you how far you are from the exact dynamics. So it has been proven in some paper that so this is the exact evolution of the exponential of the internal, and this is your ansatz. And you can show that it's bounded by this the value of this loss, which is input by taken on the scope. Okay, so all of this is nice, but the big problem is that how do we find the minimum of this loss? And it's very noisy, and it's really the core of my work recently is how can I make a better strategy to optimize this loss, having said that it's a nice thing to solve dynamics and not the stuff. So one thing we can do, of course, is in the sense we can estimate the gradient with respect to the parameters of the loss to find the minimum. But there's a problem is that it's very difficult to find the minimum of this. In one situation, especially where it's difficult, is when the window becomes larger and larger. So I told you that we optimize on the interval, and here on this plot, you can see that. So each of the colors corresponds to the loss optimized on a given interval. So on the yellow thing, we saw the dynamics only up to 0.1, and then for each color it's up to 0.2, 0.3, 0.4. And you can see as we increase the size of the interval, the precision at which we are able to approximate the dynamics dramatically decreases. Like already this value is not that good, but here we are completely off. And you see, like compared to the exact references, you start to deviate a lot from the target and the subtotal. And so this is a major setback. Like we said, we have a very nice loss, and that can give us the dynamics without all the previous problems. We cannot optimize it, so we have to find another way. And what I want to introduce is what we call natural gradient descent on the turbulent methods. And it aims at answering one of the main problems of gradient descent, is that it has no structure. So basically, you move into your parameter space, and you want to make small steps. But you never know that maybe if you move a little bit the parameters, then your ansatz, for example, the derivative changes completely. And then you are completely off, and your loss increases a lot, and we didn't plan on it, and so it can result in spikes, instabilities, and literally more like preventing the convergence. So the idea basically is that if you look at this loss, you see that as a function of psi, it's something quadratic. So you say, maybe if we minimize the Hilbert space, so if you take the gradient with respect to psi and its loss, the function of derivative, whatever, you can think like if I follow this direction in the Hilbert space, I manage to converge much more efficiently than in parameter space. So we said we don't have any structure and we can anticipate all the moves in parameters, so we won't lose the loss. Okay, so now we want to, the goal is to approximate the Hilbert space gradient. Okay, so just some definitions, which are also important. So we work on the space of normalized trajectory, and we use the main object to consider at some point of psi in the space of trajectories in its tangent space. And there's another thing which is called the variational tangent space. Basically, it's the span of all the derivatives with respect to each parameter of our ansatz, is called vi, and that are included into the tangent space. So they don't span all the vectors that are orthogonal to psi, which corresponds to the tangent space, but they span subspace of it. Okay, also introduce the differential of M, also called the pressure derivative, which is a linear form of the tangent space. And we know that if you have some linear product V, that could be here V, so I introduce a linear product because I need a notion of distance here in the tangent space to because ultimately we probably need to approximate this gradient. And even in the product, we can find a representative of this inner form, which is called the Hilbert gradient, basically. So we can plot the differential like this. Okay. So here's a picture to visualize. So we have the trajectory on the sphere. So on the side, you should begin to trajectories. You have this tangent space, and you have this continuum, which is the directional tangent space. That is the direction we are able to resolve in the Hilbert space with our parameters. Now there is the Hilbert gradient that most likely won't be parameterized by tangent space. And the goal of our method is to prospect back as accurately as possible to inside our variable. Okay. So in a sense, if you look at gradient descent, it's already a projection of the Hilbert gradient on the vertical tangent space. So we can write the gradient with respect to parameters like that. So we have this new product, the Hilbert gradient, and you have this expression, the vi that the derivative with respect to each parameters. But it would be nice if the vi, for example, would be orthonormal, then you will know that this is the orthonormal projector, which minimizes the distance to what we want to resolve. But in general, it's a very bad choice because if you are redundant directions or if in some parameters you don't move at all, you move like depending on your basis here, this can be a very bad or very good projector, and most likely it's not a very good way to approximate the Hilbert gradient. So now really our problem is this. We want to minimize the distance with the subject with respect to the norm defined by our inner product. So it's equivalent to doing the orthogonal projection onto this parameterized space. Okay, so this is just a least square problem. And in general, you will end up with this equation for the optimal coefficient if you write your target as some combination of times with rational tangent space. And you will see that if you're familiar with this method, these equations are exactly similar to what you get when you do TGVP or what's called the stochastic configuration, which is basically rational multiple for one. Okay. So there's still one unknown in my method, which is what inner product do I choose? Because it's literally what's going to determine which representative in the variational tangent space I choose to approximate the Hilbert gradient. If some distance are off or lost, it means that it's not a good choice. For example, there are two choices I could make. So this is the N2 inner product, and this is the H1 sub-F inner product. So one involves only the, let's say, the wave function, if you want to think about it in Hilbert space, and this involves also the derivative of the wave function. But one is better than the other because if you think about it, imagine you make a small moves in parameter space that completely offsets your derivative with a high frequency oscillation but low amplitude. Then these two states will be closed for the N2 norm, but their derivative will not be closed. So in the H1, these two states will not be closed, and also for the loss, remember the loss involves the derivative, and so if you change the direction in which you're pointing, this means that you're not making a good move. Like, I mean, for example, if this was solving the dynamics, then you have a lot of fluctuations that maybe it's not so good anymore. So this is why, for example, this metric could be a better metric than the other. But there's an even better choice that you can make. So if we introduce this operator L, which is the operator such that if you look at the Schrodinger equation, basically it's L psi equal to 0, and the loss as the structure, it becomes literally quadratic. And if we do a little perturbation in the tangent space, we can expand the loss like that, where we recognize that here we have a particular derivative, and here we also have the second order derivative of the loss. Yeah. And the fact is that if you look at this object, so basically, if we look at the blue part here, it's because we have the new parameters on the software and not complex. But if you look at this object, it will define a positive semi-definite form, which can be used as a metric on our space. And what's nice is that if we use this, we literally know that if we move in the parameter space, how much will we move in the loss? So if we represent here like the parameters, suppose we make it move in the direction V, then this will tell us like, okay, maybe then the loss will be very large in that direction if we don't want to go, whereas if we go in some other direction, the loss will be minimal. So literally, this is exactly what we want, because we want to know if we make a move, we want to make it in the direction of decreasing loss, which is the main problem of gradient descent. If you make a move in parameter space, you never know, maybe if the loss will increase or if it's going to go into a flat valley that is not a good direction we want to go. Okay, so this is what we're going to use. So I skip all the implementation details because it's a mess to do. But let's look at some results. So we already talked about it earlier. So the transverse field ID model is some standard benchmark where we want to evaluate methods. It's a very fairly simple Hamiltonian. We have most of the coupling and the transverse field in the x direction. It gives rise to fairly complicated dynamics, especially if you take it at its critical point. So usually we quench from the one state at h equals infinity that we call the plus state. So it's like a state of and if we take it to the critical point, the dynamics become very complicated to approximate all the spin oscillates in a kind of chaotic manner. So it's quite challenging even for numerical methods. 1D and PS can do very well, for example, but it's still very challenging. And for example, here I cut the residual, so the lobs at each time through training on different length of the interval. So let's say I want to approximate how many dynamics up to time 0.25 this result, and then up to time 1. And I compare so natural gradient descent, which is the full curve, and the first order gradient descent optimizer, which is called ALAM, which is the dash. And you can see that indeed it helps to resolve a lot, improve a lot of the results, like up to literally several orders of magnitude. And also it helps to converge faster. So for example, if you look at this plot, this is the convergence on 0.25. This is the time it takes to optimize our network. And you see that after like 100 seconds, you already are to the value that you get with gradient descent up to like, more than 10 or like 50 times the time it takes to arrive here. The convergence is very steep and very fast. And one nice thing that you can see is that it seems that when you do this method, the network tends to kind of optimize in a region where the loss is very small at the start and increases as you go to the end, which is nice because there's a big problem in that method is that imagine the loss that you get at the beginning is very high, then everything that you get after that can be meaningless. Like, if, for example, you can make a very big mistake, then you collapse in an eigenstate of the dynamics, and then you have a loss here that is 0. You make 0 error, but you make a super large error at the start. So technically, this the end of the interval has less meaning than the beginning if you make some mistakes. But here you see that it kind of stays increasingly, so which is something that kind of reassuring. And also, it can find very nice solutions if you look at very large windows, which are like I said, harder to optimize. Okay, so just a quick outlook. So this is like a method that can help solve the Schrödinger equation with this so-called lower quantum states in a way that kind of could solve the problem that we had with the traditional method, and also at a lower cost, hopefully. Also, this algorithm can be applied to solve any equation defined by f psi equals 0. Like if you think about, for example, imaginary time evolution, this would like if you do like a purified with the ancilla, whatever, like you can do that. But there are still some problems that I kind of covered in that presentation. Is that even if you have a nice algorithm, you are still you're working with exponentially large spaces, so you have problems in stochastic estimation, which I think completely destroy the benefits of your algorithm. And also, even if you also have to do a lot of engineering, for example, what ansatz you want to choose, which is something pretty much unexplored because we don't know something like thermodynamics entirely. It's something not so clear. And also, every parameters of the optimization has to be tuned pretty well if you don't want something that explodes or something that doesn't come back. Okay, so I think with this I'm done. Thank you for your attention. Let me know if you have any questions. Yeah.
So on page 11, and also before.
Okay.
Yeah, it looks really like TDP, and then you later you said that this is like TDP. And can you? I just want to do this. You can use TDP to gain access to the excitation spectrum, right?
Yeah.
Can you just do the similar thing here, and then see how to reconstruct from your given initial states the spectrum? Just perturbing on, I don't know what the mathematical structure is. Is it a manifold of which the neural states lie, and then you perturb at the ground setting?
You mean accessing the excitation spectrum, just like you presented?
Yeah.
I don't know. I mean, basically, we have the same. I think it's like because here we try to, like in the paper, you will get each side, and here you will get your perturbation in the virtual manifold. And so you want the perturbation to closely follow each side by doing orthogonal projection. I think it might be possible to compute the excitation spectrum once you have the function back the full dynamics once it's solved. But I don't know if you can do the techniques that you did, because here, like the manifold, it's really the one of the full trajectory. So
yeah. Because the manifold's really trajectories.
Yeah, exactly. Yeah. It's really like we optimize on basically this stuff, like we have a set of trajectories. Yeah, exactly. It's not just the bare Hilbert space anymore. That's
probably.
It's more probably we have to. Yeah, it's not trivial like this. Yeah, definitely. I mean, probably like you can think that if you have access to really the continuous trajectory, maybe you can compute some observables that wouldn't be possible if you only had like snapshots in your version manifold. Maybe. Yeah.
So, a question about the long time simulations.
Yeah.
So you showed some data for kind of a short time.
Yeah.
How does your method behaves at very long evolution times? I know that, say, if you try to do, say, tensor network, at long time they suffer about entanglement.
Yeah.
How does your method behave?
So there's one big challenge is that you see, like, you can optimize only short windows. So if you want to optimize further, you have to freeze one window and then you start again from the initial state at the end of that window. You optimize further in time. So in that way, we also accumulate errors because of that problem that you are still limited in large windows. You can say, okay, I want to solve the dynamics up to time, I don't know, 50, and then it works. So it's true that as time grows, we also have issues. I don't have any it seems like at least the optimization also becomes harder and harder if you optimize, for example, the same interval at all the time. So maybe it's still true that neural states they still have issues, or like the dynamics at longer time is more difficult than the one, for example, like if you do 0.1, three of the states will not change a lot. And as you accumulate, you have also errors. Like, for example, one thing is that neural networks are known to have a hard time approximating high frequencies. So if you have longer dynamics, maybe you will have a higher contribution of error when frequencies being not correctly approximated, and so this can throw you off. Also, it gets harder with time increasing. Also, like it's not magical. Yeah.
So the T is in units of the Ising parameters.
Yeah. So here, it's in general we put each T here, H equal 1. So,
one of the comment is that in this, so in one variance of this work, because now you have the solution, you can also, when you optimize 0 and 5, can query your solution at all the times. And by doing some, let's say, black magic, we are able to put things what we don't get were high frequencies, but small frequencies seem to get right. We can extrapolate it in time, which we have used to look at thermalization from. So where we saw that we match with quantum Monte Carlo, where very but we're seeing some deviation, like in this model, we see that it doesn't thermalize. Now, we don't understand the limitation of that.
That's a 1D process field.
That is
Yeah. Yes.
So I was wondering if you try or work together with this.
So basically, this is a stochastic recombination. So you mean so in the situation for instance? So equivalent of the Fisher would be if we use the L2 distance. Because the Fisher, the quantum geometric tensor that we include in the special, we have this metric in the Hilbert space. This would give you like we have the quantum geometric tensor, and if you take the parameter update, if you take the inner product in parameter space associated with this tensor, it will result in the L2 distance between these two wave functions. So this is it, but I tried using it and we saw that it wasn't helping much. I think maybe because of the problem and that we actually, maybe for ground state it helps because the Hilbert space is a different space and also the objection is different. But here, because you also need to take account the derivative and so on, and this was really giving the best results. Yeah. So this, I think I have like also 16 screens. And because you have to approximate the dynamics, I'm trying to throw a lot of parameters, maybe not a very efficient way, it was like 10,000 parameters, something like that.
And like if you initialize how you
yes, that's some problem that we can have. So, I mean, here they will initialize randomly, but when you try to especially go at longer time, we recently saw that initialization indeed matters a lot because, especially because you have to like respect some initial conditions that can be, I mean, the way we have the answers right now, it's a little stable, and so if we initialize badly and the loss starts from a very high value, it can have a very hard time to converge or be very unstable in the first steps of the optimization. So one thing we can do is that, and Filippo mentioned that we can kind of extrapolate the dynamics at long time using the specific way of doing the ansatz. And so what we do is when we finish an interval, we extrapolate a bit to the next interval and try to fit it to our extrapolation, which is not very precise, but it is also starting point that we quite low and stabilizes the optimization also. But it's true that it has been an issue that, like I tried to optimize, for example, up to 1.5, 2, and then at some interval, the initialization is just super bad, and then it explodes the optimization with the more convergences problems. Yeah. Especially like one big problem is this one I quickly mentioned that because you know the dynamics it can collapse into an eigenstate and have a very high peak at one point. So this is like the biggest collapse that I had at the initial. We had the initial state and then because my initialization was bad, then everything collapsed in an eigenstate, and so I just had one spike and then zero everywhere. So it's a big problem.
That's a network, so you're going to state the number of parameters or power of each and whatever. Here we are linear in the number of parameters. It's really not the dominant form.
Yeah, and also like this. Sorry.
you have any idea how the error at the end of like the time window scales with how big this time window is? Like obviously take a smaller window over which you optimize dynamics, the error at the end is smaller.
Yeah.
Do you have any idea
of the scaling? I mean, there is. I mean, the only scaling that we can make, I think, is sorry. No. This one. But then about this object in itself, how does it scale with time? I don't know because it can depend a lot on parameterization and maybe we hope that we can find better parameterization that allow to improve larger windows. I think in general we can say a lot about that. It's that's really kind of a problem because we like to know maybe okay if this given that we can only go so far like a bit we want the control interest, okay.